Okay, we will start our WebEx session for this afternoon. We have 2 lectures to go through on the topic of interchange, pooling, auctions, and so forth. I apologize. I got way behind, and over the weekend I realized, and so I hurried up and did the solution for 6 and the solution for 7. Those are now posted. Chronologically I did 7 and then realized I had never done 6, and I equally apologize to our poor TA, Hunjin Choi, because I don't know how he graded them. Normally he's the reminder. He says, "Professor, can you do the solutions so that I can grade?" But anyway, he didn't complain. So anyway, those are now posted on the Google Drive for you. Homework 7 was due way back on the 10th. Or no, homework 7 was due not the 10th. That was yesterday. Was due last week, and so homework 8 has been posted. The homework 8. One thing I'm gonna indicate to you is read the manual. It's quite tricky. The one thing that's tricky about this, you're going to run the state estimator. So on my computer, I set up 2 windows. This is the way I do it anyway. And so I don't know what to call this. This is the MATLAB work area, and this is the MATLAB editor. Once the programs are all running, you highlight the program you're using, and then you hit the one button and then it runs it. When you are running, you've got to start out, and then as soon as you run, you're going to get a window, that asks you for the file. Ask which spreadsheet to select. Sometimes there's only one. In this case, the measurements file is always the same file, but I ask you to run with 2 different cases where I've purposely fooled around with the load. But anyway, and you'll see that in the directions. But so there's one for the network data, and then there's another one for the measurements data. Okay, when you start the measurements data, and you're going to get a small window over here. On my screen it just pops up like this, and you get this is a little button window that you can click things, and when you've read the measurements in, then you can edit. And when you're done editing, then it says, okay, now store the measurements. And there's also in the manual, it explains carefully when you're doing a power flow at the first thing you do is you get a power flow, so you get that on the screen, and then you get it stops. Okay, so that's what I want to say. It comes down and it gives you all these lines, and then it stops. And when it stops, it says pause. It may say pause at the bottom, but it's actually a command in MATLAB to pause, and that's so that you can look at what's on the screen. Because if you don't put the pause there, it'll fill the screen, and then boom, it goes to the next thing, and that what's on the screen just goes off the top. Now, if you're looking at if you're running a printer, you don't care, okay? Computing when I was your age there was no screen. Everything was out on the printer, and at the end of your session that you had on the computer, you weren't sitting there. You submitted a program either electronically or you could do it by card deck, and you got a big stack of printout. But here we're watching a screen, and it goes zing. But by the way, these two windows, I highly recommend if you those of you that have a laptop can't do this, but you see this, if you get a nice desktop, or if you just connect this to your laptop, get a big monitor. Get it like a 27-inch monitor. Yeah, it costs a little bit more, but then you can have two windows side by side. That is infinitely handy, having two windows. If you were in my office, you would see two separate displays. They're mounted on these. They're not robotic arms, but they look like robotic arms. Big heavy metal with movable joints, and so I can orient them. I have one that's oriented horizontally, the other way. It's much better if you just have it on one screen. Get a big screen. 27 so far is about as big. You can get bigger ones, but then the cost just zooms. 27 is a great screen size. Okay, so much for that. The point is, you click you have to have the cursor. Okay, there's our little cursor. We'll put an asterisk there. You have to have the cursor on this window. When it's paused, everything's stopped. You have to have the cursor over here, and then you click it. Okay, and then it goes. It says, "Oh, I've just had an input," and it does the next step. So you just so you know that. And there's various little windows that come up. That is explained in the manual too. There's a program. Let me explain this. The state estimator has a power flow, which calculates all of the P plus JQ load generation injections. And all P plus JQ flows at each end of each line. So that sort of says that's what the power system's doing. Then you have a program called SCADA. Now, when you run, I recommend that you just say run all. So you have run, let's get it so you can see it here, I'm sorry. Run all, and that's the one that you run. And run all will run the power flow, and then it runs the SCADA. And what SCADA does is it reads the measurement spreadsheet file, and then it reads all of these, the P plus JQ injections or flows. Actually, this thing also calculates all voltage values and phase angles. So it reads the injections, the flows, the voltages, and the phase angles. It just reads everything in. Wherever it says there's a measurement, it goes out to the power flow and says, okay, what is the value of that? And it puts it in memory. So now it's got a picture of the power system as a SCADA system. Supervisory control and data acquisition. DA is the part we're interested in. Then you can add noise. And we take the sigma that's specified in the measurement data, and we produce a random noise proportional to that sigma, and we put it on each measurement, okay? And you can also edit measurements. Unfortunately, one of the things that I discovered as I was doing this that I probably should have put in there was to be able to turn the measurement status on and off, but I didn't do that. So We can't do that, but you can edit the measurements. That means you literally change the P or the Q or the voltage magnitude or a phase. You change the value in there, and then you store it. That's the final step at the end. At the end is you store it. So you've read the measurement data, you've read off the power flow, you've added noise, you've edited if you want to edit certain values, and you store it. And then finally there's the state estimator, and it has two choices, two buttons that you can press with bad data detection or without bad data. I should say detection. Sometimes you just want to run it to see if it's going to run at all. Forget bad data, but normally you run it with the bad data detection. Okay, so it's a bit complex. Now today I'm going to give you the history of the history of power business from 100,000 feet going 800 miles an hour or something like this. Here's what I want to talk about. Little power system history. Okay, in the beginning, Thomas Edison, he would build a steam plant, and he would have DC, and he would have houses. Here's houses, and he would just connect them, or businesses or hotels. So maybe he had a big tall one that was a hotel or an apartment, whatever. And he could only go so far, and then he'd build another one, and he'd have DC and so on and so forth. So he'd have all these things. The 1880s, okay, 1884, 5, something like that. Along comes George Westinghouse, and especially Nikola Tesla, the brains behind it. Westinghouse was the business genius, and they came out with, so we'll say Westinghouse Tesla. Here's Edison, in the beginning anyway. So Westinghouse came out, and so out he comes from a power plant with AC, and he goes through a transformer, and he comes out, and he's got he's got these big high voltage lines. Wallenberg always draws three-phase lines. He's got I've got to educate the public that transmission is done with three-phase lines. So we go through high voltage, and eventually we come down to another transformer, and we come out again with three-phase to a distribution system, and then eventually drop it even lower voltage to houses and businesses and so forth. So this allowed larger distances. So this allowed, let's say, hundreds of miles. They weren't done that way at first. The other thing that happened was that you would have these power companies going in, and there'd be a power company over here, and maybe it would serve a small area, and maybe you had to go several hundred miles before you had another one, and it was just a power plant that supplied power to an industry, maybe to a coal mine to run pumps, electric motor pumps to bring water out of the mine or something like that. Isolated power systems, and I might say isolated companies. Eventually, they got to the point where you did have in a few cities you had the red power system, and you had the green. See how quickly I can switch between. And this guy would have some transmission lines. So we'll put some green lines coming down the street, and on the other side of the street were red lines. Maybe I'm not showing the transformers here. And here's your house, which, that should be a different color here. Can't make the house biased towards one of the companies. And so he has a choice. Well, you can imagine that it didn't take long for people to say, this is a complete waste of money. We're building we're building 2 sets of transmission distribution, one for each company. I don't think so. Today, obviously, there's no analogy to that other than perhaps gas pipelines, believe it or not. Houston Lighting and Power back in the 1970s had power plants with multiple gas pipelines going close enough to each plant that they would have feeders coming in from the plants with valves in them, and they could choose to buy gas from any one of those suppliers or any combination, I guess, in some cases. So that's different, partly because here this is up in the air. People don't want, can you imagine 2 different power companies, wires up in the air, and then you could wire to him, and then he gets too expensive, and you say goodbye, and you go wire up to him. That's not. So these guys decided that, look, we will go to a regulated system, and the regulated system within, let's say, a state, there's could be one power company, but let's take the state. We'll say the state had a couple of different territories. Here's one territory. Within this territory, this is company A, and over here, bigger, is company B, and here's company C. Company A builds their plants in this territory and runs the transmission in this territory, and any load that's in this territory belongs to him and gets their power from him, period. If you don't like the prices, then pick up and move. Literally, pick up and move. Or whenever you're going to put up a new power plant, let's say a new business, a new factory, start negotiating with these guys, and the best deal you get, that's where you build the plant. So there's competition in that respect. Well, and the state would come along and say, okay, now since anybody living here has to buy from you, well, we're gonna regulate the price. We're gonna fix the price, and that means that you can't charge more than we say. And the power company said, yeah, but that's better than building duplicate transmission lines all over the place. It'll save us a lot of money, and they worked it out with the state governments that said, we'll let you charge enough to cover your costs plus a reasonable rate of return on your investment. Worked beautifully. Honestly, it worked beautifully for, let's say, 80 years or so, maybe a little less, something about like that in the United States. But it began to, and then it changed, and that's the topic for next week, is the deregulation when we did things differently. But what I'm going to talk about today is the fact that, let's see if this color will show. I don't think it will. The fact that he might be high cost simply because he doesn't have access to gas, or he doesn't have access to hydro. He might be low cost, okay, and he might be middle cost. Well, if I'm the high cost guy, I'd like to buy power from the low or the mid. And so these companies, although they were responsible mainly for buying power and selling power to their customers, they built transmission lines that crossed. Okay, and I'm just going to draw one line. And these lines are just simply called interconnections. Interconnections. And so each of these lines is an interconnection. Obviously, there's more and more of them. And they're usually high voltage lines because these people are covering a whole big state. They're not going to run distribution lines for hundreds of miles. They got to run them at high voltage. Well, now we have the issue of, see, if his generation is high cost, he'd much rather not run one of his plants or back it down and buy cheap from these two guys. And the topic of today's lecture is how do you do that? How do you allocate generation to each of those power companies? And what I'm going to show you here, so we started. Let's say we started in the 1800s. I set up here Westinghouse. This is the 1890s. This kind of thing. Let's bring it up to the 1920s. Okay, electrification was moving along rapidly, but there are parts of the United States that never actually finished receiving electricity until after the Second World War, to the 1946 to 50 and so forth. Rural areas and very, very small towns that were out far away from everybody. The government set up power companies, they still exist, to serve farmers that are spread all over, the farm states out in Kansas, Nebraska, the North and South Dakota, those the breadbasket of the United States, if you will. They may not have gotten wired up until after the Second World War. It took a long time. The cities, of course, received, and these companies were now in existence. They built interconnections. Now the interconnections have wonderful benefits beyond just the guy with high cost generation buying from the low cost guy. He can save money. He can make money. So economically, but again, if the low cost guy suddenly loses a generator, he can have these two companies back him up with spinning reserve of their own. So the overall system is more reliable. It is more reliable. People, we hear a lot today about microgrids, and you can quote me on this. You can quote me on this. I still predict that you will not find microgrids in the United States on a normal operating basis, day by day. You might find a microgrid that's there that comes into its own when there's an emergency. Princeton University had a microgrid during the big hurricane that hit the eastern United States several years ago. Well, the power system went down. Princeton University had a diesel genset. They opened up the breakers and the campus had some power. It didn't have enough to do everything, but lights and maybe some of the necessary heating, air conditioning equipment. That's about it. That's microgrid, but they're not going to operate that microgrid on a daily basis and not be connected to public service electric and gas in New Jersey because the microgrid is not economical. There's just more and more talk about that. But the electric companies figured it out 100 years ago, that interconnecting and having a bigger system was more reliable and more economical. Okay? Building your own little system, okay? You hear people talk, well, suppose I build a microgrid out in just for my farm. And my response is, What are you going to do if your diesel genset or whatever you're using fails? Your wind generator fails and it's dark. Where are you going to get power? And the answer is, well, I'll reconnect to the grid. Well, are they going to let you? Are they going to keep the equipment maintained right up to your boundary of your farm at no cost to you, and be there for standby power all the time without charging you? I don't think so. So you've heard it from me. Now, if you're talking about a microgrid in an undeveloped country where there is no grid, that's a different matter. That's fine. I mean, that's good. I also have a student that does some work where they talk about microgrids or grids like that for military bases that are out in the middle of nowhere, and they fly in or truck in diesel gensets and batteries and so forth because they have to operate a lot of equipment, and so they build a micro thing. That's certainly legitimate, but not in the middle of the United States on a profit basis. If you ever hear about somebody operating one on a daily basis, please let me know. Okay. All right. So here's a little history, which I think is very. I'll put this in the notes. I dug this up today. I just put in Google. I said history of the Pjm interconnection. So we'll put this up here. Pjm. Originally, this stood for Pennsylvania, New Jersey, Maryland. That's the way they wrote it out. But you can see that they started out in 1927 as something called the Pjm Interconnection. That is the world's first continuing power pool. Now, what we're saying is that companies like this decided, look, we're going to do something to organize ourselves so that we can transfer power and we can operate at the most economic way possible, and that was called a power pool. PJM, they form under that name when Baltimore, there's the M, Maryland, Baltimore Gas and Electric in Maryland joins them in 1956. GPU stands for General Public Utilities. Okay, well, I'll write that in. General Public Utilities. PJM installs its first online computer. I was just starting. My first job. I worked in this industry in 1966. This is a bit of a misnomer. This is PJM glossing the history a little. They installed the computers, but they didn't have the software, and they weren't operating for a long time, and that was still undergoing completion on my when I was still working in Pennsylvania. But yes, they did install computerized system. PICO is Philadelphia Electric. PJM completes the first energy management system, 1968. Okay, I will accept that. So that's when they were working on that. They used mostly IBM equipment. Atlantic City Electric, Delmarva. These are two companies, one in New Jersey, one in Delaware. PJM Interconnection Association forms. Now, PJM launches its first website. I don't know why they put that there, but this is the date. Actually, it's 1996. So we'll just put a big break across here. Down here, everything is regulated. Okay, from the beginning. From the beginning, it's regulated, and we use the term deregulated up here. And we will explain a lot about what that means next week. In fact, we can come back to this. But there's other companies, and PJM has moved all the way out the utility in Chicago is now part of the PJM system. I will say this too. PJM was, and to some extent still is, considered the technologically the leader in the United States. I won't say in the world, because right away everybody from France will jump on me. The French have a very, very sophisticated system at EDF, but the PJM is considered one of the premier systems. It was one of the first and the premier operated power pool in the U.S., and same thing for PJM down here is a pool. PJM becomes an independent system operator. Remember, that's the term the U.S. uses for transmission operator, which would be a much better term, but they don't use it. That was the word independent had to be in there to satisfy, I don't know who, the courts, whatever. But it became an ISO, and actually they say later on an RTO, Regional Transmission Organization. So we'll put that in. But here it was a pool, okay, and so it just changed, and it was natural for PJM because they were doing all of that stuff. They are on the outskirts of Philadelphia. They have beautiful control building, a control center there, near Valley Forge, Pennsylvania. That's the only description I can tell you, is that I know I was there a couple times. It's near Valley Forge, but that's just a description for the PJM. Now, what we're going to talk about today is we're going to go through the homework problems in Chapter 11, and I love this because problem 11, 1, 2, 3, 4, and 5. I don't think it covers 6, but it's an yes, it does. It covers 6. It's an interesting problem because we solved it in about 5 different ways. This is the issue, and here's the example. We used 4 areas. I don't like this diagram. We shouldn't have drawn. This is a generator, and it's connecting to these. It should have shown the bus and had the generator sitting off the way this one and this one and this one. So, but anyway, there's area 1, area 2, 3, and 4. You'll notice that 4 connects to 1. It does not connect directly to 2 or 3. The idea here is to show that areas don't necessarily. Now, area 1 connects to everybody, but area 2 does not connect directly to 2 and the 3 and 4. Area 3 doesn't connect to 2 and 4, etc. And that's certainly possible to run it that way. But this is our pool. This is our pool. Each area has a generator. Each area has a load. Okay, so this is a generator right here, and these are generators, and we showed you the value of load, and then we're going to say, okay, we would like to talk about now how to operate this 4-area system economically, and we tried to put this together in a variety of ways to show you how that could be done. And it really was a precursor to the modern RTO or ISO that we have in the United States. That is the way they did it, and different groups of electric utilities, different power pools. There were power pools all over the country. We had one in the Minnesota region up here called MAP, M-A-P-P, Mid Area Mid America Continent Power Pool, but the PP stood for Power Pool. MAP, M-A-P-P. There were power pools everywhere, all across the, PJM is in the states of Pennsylvania, New Jersey, and Maryland. At the time, there was a power pool in New York, there was a power pool in New England, power pool in the South, and so forth and so forth. And they had different rules and different ways of doing things. There was no uniform. They were all just associations so that they could all save money. And it was a good idea. A power pool. Let me get a little drink. Power pools allowed the companies to generate cheaper. They allowed them to build a more efficient transmission system, again because they didn't have to duplicate certain facilities. To increase reliability, they could back each other up, and so forth. And they were the modern precursor to the ISOs that we have in the U.S. today, and that are existing around the world. Okay, so in the homework problem, then, we have, and I'll put this in with the notes. We have this that's the same figure, and the first question, 11.1, says here's each generator's F of P function, cost function, and it simply says each generator will supply the load to its own area, and we're not going to interchange anything with anybody, and we probably don't need the high voltage lines. So there's the solution to 11.1. And when you get this, you'll be able to see that we have different lambdas. The production cost is different. Well, partly it's different because the load is different. This is the highest production cost is here on area 3, but he has 550 megawatts of load. Yes, he has the most load. And this is the load down here, and there's no what we call no interchange of megawatts. Nothing. No import or export up here. By the way, let's get it straight here. If I am an area here, area 1, and this is area 2, and the power is flowing like this. Okay, if you remember power flows, we said if power is leaving a bus, then this is positive. If power is entering a bus, this is negative. Okay, so we say this one is exporting, and this one is importing. Those words are fairly clear in and of themselves. Export means to send out. Import means to bring in, as with any trade goods. But it follows the same sign convention as power flow. Positive at the bus is export. Negative at the bus is import. Okay, so we did this, and we're going to come back to these numbers. But this is the base condition here, base, which was generator supply, his quote, and they use this term, own load. Okay, meaning the generation in my area supplies my load and no interchange. So the generation supplies own load. And we get different lambdas at the areas. Now, area 2 is really cheap, 450. Now he's cheap for lambda. Okay, that's the dollar per megawatt hour cost, and he's much cheaper than area 3, which is up at 6. But so is area 1 up at 6. He's not as big as area 3, but he's also fairly expensive. Okay, so that's the base condition. And then it says, assume that area 1 buys 190 megawatts from area 2. So let's go to my, I don't know, we gotta just juggle all this paper. I'll come back to this, but I'm just gonna say here. Okay. And I'm up to page 3. Okay. So 11.2. Area 1 by 190 megawatts, area 2. That's called A. B. Area 1 sells 120 megawatts to area 3. Now the reason we put this in here is that you get different numbers depending on how you do this. And so what we do here is for this particular problem is we say, well, okay, so I'm gonna do part I of the problem says A then B, and the second part says no, do B then A. Okay, and the transaction order actually has a bearing on what happens. The overall result are different. So we'll just put this here. Results are different. It matters. It matters. You'll notice that if I'm sorry, do I have that? Did I write that down correctly? Buy, sell, yeah. Area 1. Think about this. If area 1 buys, then he has to raise his generation. Okay? So this one simply means that area 1 gen up. Okay? Area 1 gen up, area 2 gen down. But when area 1 generation goes up, he's at a higher point on his cost curve, right? And now when he sells, he starts from a higher point. So area 1 gen down, and area 3, pardon me, is going to go up. This is this up and down over here. I mean the P from the generator, delta P gen. This is the up and the down that I'm talking about. Well, if he first goes up and then comes down, his cost changes are going to be different than if he does B first, where his cost goes down. Now he's starting at a lower cost and then he goes up. Okay. Yes, he ends at the same point. Area 1. No, he doesn't. It's a different amount of megawatts. So he doesn't end at the same... I'm wrong. He ends at the same point. If he buys 190 and sells 120, area A is a net buy of 70. If he sells 120 and then buys one, he's a net. So he ends at the same point, and so does area 2 and 3. So as far as the megawatts are concerned, everything's the same at the end of A then B or B then A. But economically, that's not the case, and that has to do with where he starts his dispatching. So I have 2 pages here, and the 2 pages here is the 11 A then B on here. And so A, you remember, A says, okay, I'm going to buy 190. So what happens here is on A is area 1 buys 190. Okay, so that means he's importing. He imports 190, and his generation goes down, right? His generation was 400, and it goes down to 210. Area 2 is selling, so he goes up from 350 to 540. So his cost, the costs change. The costs change. Okay, now this is the new production cost here. Okay, and then down here we say, well, what's the change in cost? So here's the production cost in area 1 is going to go down. Is going to have I got that right? He's going to import. So his production cost goes down because he's not generating as much. So his production cost goes down. So here's delta cost here, and here's area 2 production cost, and there's then we work out a payment system that says, okay, look, we take the difference in the two, the change in costs, and we divide it in half, and then area 1 pays that to area 2, and so area 1, his cost went down, but now he's got to pay area 2 something. Well, you notice it went down by $9.59, but he only has to pay $9.45. He saved something. He's making money. Similarly, area 2, his cost dropped to $9.32, but he got $9.45 back. He made money. They both make money. So that's important here. Both A and B make dollars. So that's good. Okay. Now let's do the second step now, and say, well, okay, let's come back here now. Okay, once this is in place, I now take the 70 megawatt transaction, and remember the next one says, okay, area 1 is going to sell 120. Pardon me, not 70. He's going to sell 120 back. Well, he's already importing 190. So if he's now gonna export, this is the interchange. This is the change from the base case. So he's back to 70, and area 3 now is receiving 120. Okay. The sum of all the exports and imports always equals 0. We're not looking at losses in here. Obviously, that would be slightly different if there were losses. So we go through and we calculate the new production costs, the new generation, and area 1's now in this case area 1's cost. Okay, it was this, but it's gonna go way up because he's now selling, right? B is to sell, so he's going to sell, so it's going to go back up. Okay, and similarly for area 3, this should have said area 3. Look at that. There's a mistake in our solutions manual. There's probably lots of them. Anyway, and we get an overall change here, and so there's a net gain. Area 1 gains 69, area 2 gains 13, and area 3 gains 55. So these are the net delta cost. Okay, they all are positive. Now along comes B then A. Remember I said that's going to be different. And if I go over that, B then A, without grinding through all the numbers, but here we did the the 120 sale to 3, and then the 190 purchase. Okay. At this point, we have the same generation. The same generation. This is identical to the first page. So this is the same in here at the very end. The generation is the same, but down here, I want you to, if I can get these net gains down here. I don't know if I can get them on the screen. I can get them on the screen. Here's the first case over here, and everybody made money. Here's the second case. He made slightly, no, he made a, this is the same. But this guy made a lot, and this guy lost. Okay, notice the negative. So the order has a big effect on who makes money and how much. Okay, who makes money and how much is very, very affected by that. So that was the purpose of that exercise, was to show the fact that there is a reason to worry about the order of the transactions, and so order of transactions has an effect on costs and profits. That's a very important lesson. Also, that being the case, the modern transmission operator, the modern ISO, doesn't do anything with an order of things like that. They have a certain time period. You put your bids into an auction, and then they do the auction calculation and tell you the result. So there's no, he was ahead of, I was ahead of him, and then this guy, and all. They used to have that kind of order problem in there, and they would do it over the phone. The operators would sit there, and their neighbor would call up and say, "Okay, I can sell 100 megawatts to you at $28 and per megawatt hour. I can sell 200 at $38, et cetera, et cetera." And then the guy receiving the phone call would come back, and they'd negotiate over the phone and agree on the price that they were going to. That was called Economy A transactions. But you can imagine trying to do it with 4, 5, 6, 7 electric utilities that you could transfer power to. Lots of problems and issues. It became very, very, very complicated. And I have to say, when they did it with the markets, I don't know, I don't remember anybody standing up and saying, this is going to make everything more uniform and simpler and so forth, but it is. And it is the way to do it. And this came from the thinking of economists, not engineers. Oh, what heresy we do speak here on in my class. It came from economists, not engineers, to go to a market, and it got rid of a lot of problems, really did. Okay, so now the next problem, which is 11.3, we'll shoot this up here, 11.3. So, okay. Central dispatch. Okay, so here we have these 4 areas. Where's my I'm going to get my here. There we go. So in this case now I've got an area like this, and I've got an wait a minute. An area like this, one like this, and here's my other one out here. And over here we put a computer, and so here's the pool office. The pool office, and I connected the communications lines to each of these generators. Okay, so this is communications. And now I can do a central dispatch. And each of the companies would have to contribute something. And oh boy, here comes the formulas again. Is it based on the amount of load? It could be based on the profits, etc. They had formulas to say who, because the pool office is a building, it's got computer equipment, it's got personnel to maintain and operate, and it's got operators, etc., etc. Communications, it's a big expense. But believe me, it was worth it for them because it can save a lot of money. But now I can do a central dispatch. I can do a dispatch that covers everybody. So I'm going to do a central economic dispatch. Okay, so the central dispatch, so the central dispatch, same as single economic dispatch calculation. All four generators, all the load is in it. And this is what PJM used to do and all these other power pools. They would do a central dispatch. Now you have an issue. It says, well, okay, there's going to be somebody's going to come out ahead and somebody's going to come out behind. How do we allocate the savings? So here's the big question. Okay, how do we allocate the savings? And so we're going to do what we call a split savings. It's in the question that says, assume a split savings pool arrangement such that each area exporting receives its increased costs of production plus its proportionate share of 50% of the pool savings. Okay, that's an exporting area. Find the cost per megawatt hour of transfer energy, that's the pool energy. And that's this next page. It looks like this. And so here at the top, this thing that I'm going to put the red around here again is the central, get it right here, central dispatch. I'll write it out. Notice the lambdas are all the same. Zoop, 9.26. Production costs. If we go back once more and we compare the production costs to the base case. So generator, this one went down. So this one went down. The second one was 350, but he went way up. And this one, the 431, he went way down, and he went just up, just a little bit up. Okay, just a little bit up. Some have to go down, and some up, and the net is the same. But now we have different costs. Okay, and the interchange is listed over here. How much did each side end up buying and selling? It doesn't say to whom. Okay, that's interesting. It's not it's not A selling to B, or 1 to 3 or 1 to 4, and it's not that. they just run it and they say, well, number 1 says, well, I'm now importing, and number 2 says, I'm exporting, and number 3 is importing, and number 4 is exporting just a little bit. So that's the net result of a central dispatch. Now, this is the central dispatch cost. Here's the delta P. These are the exporting areas 2 and 4. So there's his increase in cost was very large. It's the central dispatch cost minus the original dispatch cost. There's the delta cost over here. You have to look at this carefully. I labeled it so that you could tell on here. There's the delta cost. Similarly here, so both of their costs went up. That's the net cost increase, about 139. No, I'm sorry. I'm sorry. The net pool savings. Okay, so this is the net pool saving. This is not the sum of these two. The costs went up, and the pool actually saved money. The pool saved money. Originally, it cost central dispatch is $81.34. 79 is the. Did I get this wrong again? I am sorry. The central dispatch cost is $25.07 for area 2. That's right. And the original dispatch cost was $16.37. Okay. Now the original cost. I'm sorry. This is the problem down here. This should be $79.94.77, and this should be $81.34.07. Meaning that this difference, okay, is really negative, okay, because it's originally when you did the central dispatch. So I think I would rather have seen this with a minus sign here. In any event, the pool cost, meaning cost for everybody, went down. Well, that's good. It better. We did the central dispatch as opposed to each guy doing his own, and that should come out less. And then we said, okay, area 2 receives his cost, okay, area 2 takes the central dispatch cost, and it adds to it, we're going to allocate. And these allocations, it's the delta cost here. And you notice that I'm allocating 178 divided by 192 and 1436 divided by 192. Well, that's just proportioning out this 178 and 14. So it says, well, look, this guy is doing the most exporting, and this guy's just doing a little. So the proportion, whatever his proportion is, and then 50%. Of that, and that gives me the pool, the amount that they receive. And there's a calculation down here. It says, okay, how much was the pool energy price? Okay, down at the bottom, and that's an idea to look at that. But I want you to notice something. I want you to. This I think is very interesting. Does that look familiar? If you look back up here at the lambda, the central lambda, this thing almost hits it. It's 526, and this would of course round up to 527, but it's almost the system lambda that we get up here at the top. All right, now what I'm going to do, I'm going to stop here. I'm going to talk about the rest of this. But I'm going to talk about 11.4. We're going to make that your homework problem. I'm not going to give you the solution to 11.4, 5, and 6. That's going to be your homework 9. So we'll put that in here. Now I will write that up and I will distribute it with so homework 9, you're going to do 11 4, 11.5, and 11.6. There's several more parts to this, and this is really what happened. We had a pool in Florida. And the Florida companies, wherever they were, but there's one over on the Panhandle, and there's a couple other companies in Florida. Let's just do them like that. They had a computer system. Here's the computer here, the pool computer, and I think in the beginning they literally would enter the stuff in the computer by hand, and eventually they got to do it by hooking up remote terminals in each office. Because nowadays we do that by using some sort of secure website, but whatever. But they may even have secure communications. Another Wallenberg opinion: if it were up to me and I were running an electric utility, or I was in charge of NERC, I wouldn't let anybody send anything over the internet. I wouldn't let the internet I wouldn't allow pool computers or anybody else come anywhere near the building. Okay? So you go out and you build your own secure communication network. That may not be practical. But anyway, let's keep going here. So, and the idea here in 11.4, it says that 11.4, quote, to sell, quote, to buy. So each guy says, okay, if you want me, I will put these on, and they put them out in deltas of 25 megawatts. So I'm going to say, okay, sell 25, sell 50, sell 75, sell 100. Okay, and these are called, this is an increase, and an increase. So sometimes they call this an inc. This is a decrease. This is going to increase your costs. I'm sorry if you're selling. I get it wrong. Let's forget. They sometimes call them inks and decks, but sell. So I'm going to sell, and here's the price. The price in dollars per megawatt hour. Okay, again, we're going to assume it's an hour, so it looks like $1 per megawatt. And we give you prices, and 1, 2, 3, put too many in there. It's obviously going to be increasing. As I sell, my costs are going to go up. And I also go out and I also say buy 25, buy 50, buy 75, buy 100. And now my costs are going to go down. Okay, so they're increasing, they're decreasing. And so each area submits quotations to the broker, and that's the way they did it in Florida in this system, to sell successive blocks of 50 or 25 or 50, I guess, and purchase blocks. You could do it in blocks of 50. Here's blocks of 25. So these are 25 megawatt blocks. And these again are 25 megawatt blocks. So here's blocks, 25 megawatt blocks, 25 megawatt blocks. Or it could be 50. It could go 50, 100, 150, 200. Doesn't matter. And then they would furnish these to the broker. They would send all that in. So that there was part of the operation. Everybody sent at a certain time of day. Everybody sent their quotes. Notice that there's quotes to sell, quotes to buy. Okay. The quote to buy says, I will buy 25, and this is the price I'm willing to pay for it. I'm not going to pay more than I can generate myself, but I'm going to give you these quotes. If I'm going to sell, I'm certainly not going to sell it. I'm not going to sell 25 for an amount less. And they were supposed to price these off of their economic dispatch, so that they were supposed to literally, if you will, and we did it approximately that way in the problem. You would take your incremental cost function. Let's say here's your base generation here, base. And so you'd go up, plus 25, plus 50, plus 75, etc. Or if you're doing decrements, down here you'd go minus 25, minus 50, and so forth. And you'd get a delta cost each time. Okay. Here I'll do it differently. I'll draw it differently so it looks like it. So it's coming down, whereas here it's going up, and the price is going up. And so that's the price that you put on it. And because of the shape of this curve, these blocks up here get to be much more expensive. And everybody does that. Okay. So it says each submits to the broker, and at the prices are quoted the average incremental cost for the block. The broker matches the rules as follows. Now, in 11.4, Rule 1. Only direct connection. It's just a way to make the problem interesting, frankly. And what we did was you arrange all of the quotes. You get the individual quotes, and then you arrange all quotes. And so here's the buy. And if you're doing 50 megawatts, what we said was break it up into 25. And so there's an area, there's the size, which is 25. And then there's the average lambda. That's what we're calling the price difference, and then it's got a block number. These values are changing, and they're going up. And then we have a cell. Area, size again is 25. Here's lambda, and here's block. Okay. Now, when they're arranged like this, when they're arranged like that, it's easy. You just simply make this one buys that that block. This one buys this block. I'll just put this way. Let's see, sell. Let's put the arrow over here. And so you keep going. Okay, sell, 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 until you get to the point where the price here is greater than this price. And when that happens, you're not going to sell. I'm not going to sell. I'm not going to buy something that's more than my own price differential on that one. So that's how you do that part for, and Rule 1 said you had to do it with direct connection and so forth. So you've got 5 different ways of doing that. That's going to be your homework assignment. 5 ways. There's 11-4 has Rule 1, 2, 3, 4, and 5. The reason we're doing this is because the electric utilities, the pools around the country, around the world, really did this. Today, the pools are not uniform by any means. They're not uniform. In fact, I have a friend who works on power pools, ISO system all over the world, and he's done a lot of the designs in the U.S. I would consider him the leading expert today. And he says that he goes to Europe and he can't get them to go into a locational marginal price system. They just won't do it. If you ask why, the answer is, well, there's probably a certain amount of pride as to the way they wanted to do it, and so on and so forth. They may have some other very, very valid technical reasons, but what should happen in Europe is that they should have an ISO, which is similar to PJM, and they should operate the entire European continent on that basis. They don't. All right, be that as it may, we'll just leave it there. I would expect. I'm saying this in the face of the Brexit movement of Europe. Europe might not be Europe anymore by the time they ever got around to a power pool. Okay, so I'm going to give you this this in the notes. I'll give you the entire problem in the notes. But it is in the book, 11.1, the 11.1, 11.2, 11.3, and so forth will be at the back of as will be the solution up to, I'm going to give you 11.2, 11.3, that's it. And starting at 11.4, you won't see that until the whole solution set for homework 9 comes out. Okay? We will bid you all adieu. And who knew on last week Thursday we were going to have snow yesterday? I think a little of it's still hanging around. My 2 dogs are running out, having fun, chasing around in the snow and then coming in with all kinds of water and dirt on their feet today. It's a sloppy day. Okay, so we will leave the meeting and end it right now. Good night until Thursday.